Hello, my name is Daniel Cornel, and I'm a postdoc researcher at the VRVis Research Center in Vienna, Austria. I will present you Visdom, a decision support system for flood management that combines simulation, analysis, and visualization in one tool. Decision support is often based on simulating natural phenomena such as floods with numerical models. In flood management, the results are then used as a basis for risk assessment and the planning of mitigation measures. Here, the key to successful decision support is the ability to test and explore alternative options and scenarios. Our system is scenario-based and allows users to interactively test new mitigation strategies, change simulation parameters, and formulate what-if questions that the system immediately answers visually. Let's look at an example. In order to prevent flooding, we need to predict where the flooding is happening, which is done by simulation. In this scenario, the eastern part of this city would be flooded, causing severe damages. To prevent this, we can now test flood mitigation strategies. We first create a new scenario in our system, which is an alternate timeline, in which we can change boundary conditions of the simulation. We will first try to create a mobile flood wall along the river, which we select from the menu of available protection measures. We can now draw the wall onto the scene with the mouse, which creates a wall boundary for the simulation that we can modify afterwards if needed. We can immediately run a new simulation for this scenario to see how well the flood wall protects the city. As you can see, it protects the previously flooded part to the east, but now this part is flooded, which was previously safe. So we need to refine our strategy. In a third scenario, we now additionally create a retention basin, which is an area that can be safely flooded without causing any damages. When we simulate this scenario, the retention basin takes up a lot of water from the river, which prevents the river from overflowing its banks. And you can see that there is almost no flooding inside the city. We can now directly compare the outcomes of the scenarios by navigating through the different timelines manually. We also offer automatic aggregation and plotting of simulation results, such as the accumulated building damages over all scenarios. Domain experts then use this information to decide on the best mitigation strategy. Visdom also offers a variety of manual analysis tools to further investigate the simulation results in an interactive and visual way. For example, a user can quickly query the water levels at measuring points, areas, or buildings and compare their evolution over time. To inspect the flooding risk of a building of interest in more detail, the user can bring it to focus and assess which parts of the building are most vulnerable to flooding. This is especially helpful for the protection of important buildings, such as this hospital here. To plan the protection of individual buildings or areas, we start again with the creation of a new scenario to test protection measures. In this case, we will test a short-term protection with sandbags, which we select from the menu of available protection measures. Possible sandbag barriers can again be drawn directly onto the 3D visualization and are then transformed into physical objects in the simulation. The effectiveness of these barriers can then be tested immediately with the simulation. The simulation also allows the system to automatically calculate how high the barriers have to be and how much construction material is needed for them, which allows for accurate logistics planning. Our simulation is a validated, mass-conserving shallow water simulation using the finite volume method. It is grid-based and uses our own second-order numerical scheme to solve the shallow water equations with high accuracy. An efficient GPU implementation allows us to run simulations many times faster than real-time and makes this one of the fastest flood simulations available. To set up the simulation, we need input data from external sources. The first input is a digital elevation model defined on the simulation grid with a cell size usually between 0.5 meter and 5 meters. Second, we need the meshes of buildings and flood protection structures. They provide a geographic context for orientation within the scene, but more importantly, we treat them as wall boundaries for the simulation. Additionally, we use two-dimensional vector data in the form of polygons and lines that contain land use information, such as parks, forests, and streets. From these, we derive simulation parameters like surface roughness, which influences how fast water can flow across a surface. And finally, we add simulation parameters like inflow and outflow conditions or precipitation rates that we get as functions over time. These can be either set up manually or imported from historic events, live sensor data, or prognosis services. Visdom is able to handle geodata on the scale of an entire country. This allows us to provide a unified workflow for flood risk assessment for all rivers and streams. To set up a simulation in a region of interest, the user simply selects the region on the map, which automatically creates a simulation domain. Inflow and outflow conditions of rivers at the domain boundaries are derived automatically so that the user can start the simulation right away. This greatly reduces the overhead of manually processing geodata and setting up new case studies. Visdom does not only handle river floods, but also other flooding incidents, for example, heavy rains. In such scenarios, it is particularly important to see where the water collects and forms small streams. Flooding by intense precipitation is becoming very important in flood management because the intensity of such events and the damages they cause are increasing. To make our simulation as accurate as possible, we couple the surface runoff simulation with models for infiltration and interception. For the infiltration model, we derive the infiltration potential of the soil from the input data. Likewise, we derive the interception capacity of an area based on the vegetation density. The coupling of these models results in a robust and accurate simulation of heavy rains and flash floods that supports decision-making in flood management. This also makes it possible to investigate the concept of a sponge city in our system. It is possible to define the entire simulation domain or a particular model region as a sponge zone, which has a very high infiltration potential. The purpose of such zones is to capture water where it falls and prevent surface runoff. The effectiveness of this zone can be seen immediately when comparing the simulation results to the initial state. Of course, we also couple the simulation of surface water with the sewer network. This is a two-way simulation coupling where the sewer network takes up water from the surface through storm drains, but the sewers can also push out water to the surface if the pressure in the pipes is too high. Visdom allows the user to visually explore such situations and is a valuable tool for the planning of sewer network expansions. In conclusion, our system combines a comprehensive, state-of-the-art flood simulation with on-the-fly analysis and interactive visualization to support decision-making and provide a solid foundation for integrated flood management. Our simulation is reliable, scalable, and flexible, and can be used for a multitude of flooding incidents, be it river floods, dam or dike breaks, heavy rains and urban flash floods, sewer overflows, as well as coastal flooding and tsunamis. This concludes the short introduction to our decision support system Visdom, and I thank you for your interest.